Hello, welcome to our quarantine lecture, as I'm calling these now, they're quarantine lectures. So welcome to our quarantine lecture. This is our Thursday, April 23rd lecture. We're going to be covering section 5.3. Thank you so much for being here live with us. The advantage of this is that you're getting it done with all your classmates together, and you can ask questions during our lesson. But if you can't join us live, that's okay. I do post these videos on YouTube so that you can watch them in your own time. All right, so thank you so much for being here with us. To begin, are there any homework questions of anything in chapter 5, section 5.1, 5.2?
Yeah, actually, I had a couple
Yeah,
questions.
sure.
I sat there staring at these for like an hour, and nothing I was doing was working. It was
It happens with these.
5.2,
Mm-hmm.
and it was numbers 7 and 9.
Okay,
Yeah.
that is okay. Any other ones that you want to add to that list? It can still be from section 5.1. As is working through these, I know we all work at different speeds, and also we have different altered time schedules. So anything through chapter 5, as we move into chapter 6, in like 2 weeks is still fair game. Anything that's test 3 material, chapter 7, 6. So anything from chapter 1, 5.1 or 5.2 that you want to add to this list? Okay, we'll start with those two. So I'm going to go ahead and share my screen. So get ready for class, make sure you're comfy, got your drinks and your snacks ready. I'm going to mute all of you, but if at any moment you have a question during our lecture, just unmute yourself and ask away. Okay, so this recording, and as always, I'll post it on YouTube. So we had a question on 5.2, 7, and 9. So let's go back to 5.2. Seven. Ooh, that looks like a monster. All right, so our question is, we want to make sure our right-hand side and our left-hand side look the same. Whenever you're going through this, maybe it's worth our effort to look at them separately. So all of this is our left-hand side, and all of this is our right-hand side. Which one looks more complex? We want to work with the more complex looking one because that would be easier to break down and make look simpler. So our left-hand side is the one we want to work with. It looks more complex. Okay, so let's begin there. So I don't know what to do, right? But I see that I'm being asked to add, and I have two different denominators. So why don't we try to start off by getting that same denominator on both sides of our equation. So let's do that. So for our first equation on the right, our first term, each one of these is a term. I'm going to multiply it by the denominator of my second term. So to top and bottom, I will multiply it by 1 plus sine of x. And that's to my first term, which is 1 over 1 minus sine of x. And I have plus, going to multiply top and bottom by the denominator on my other side, 1 minus sine of x. So 1 minus sine of x, 1 minus sine of x. And I'm multiplying that by 1 over 1 plus sine of x. Okay, let's go ahead and simplify. So for my numerator, it's being multiplied, so I have to multiply these out. And that just gives me 1 plus sine of x over 1 plus sine of x times 1 minus sine of x. That's difference of squares. So it gives us 1 minus sine squared of x. Now for our next term, I have plus, and I multiply these two, so I'm left with the numerator 1 minus sine of x. My denominator, if I multiply these two, it's difference of squares. Notice we have the same term, but they're conjugate to one another. There'd be 1 squared, which is just 1, minus our second term squared, sine squared. Okay, now that I have the same denominator, I can write them together. So let's go ahead and join them and write them together under the same denominator. What is our denominator? 1 minus sine squared of x. Let's go ahead and bring that together so that we have 1 plus sine of x plus 1 minus sine of x. Okay, we see that sine of x minus sine of x, that adds to make 0. So what are we left with? We're left with 1 plus 1 is 2. So 2 over 1 minus sine squared of x. Okay, whenever you see your squares, well, what do we want, first of all? We want 2 secant squared. Okay, so I have the 2, right, in our numerator. We have that 2. How can we make 1 minus sine get us to secant squared? Well, we can use our Pythagorean identities, right? By our Pythagorean identities, we know that 1 minus sine squared gives us cosine squared. So we can change all of this to just a cosine squared. Okay, so what do we have so far? We have 2 over cosine squared x. Okay, I can split this fraction so that I have 2 times 1 over cosine squared x. And I can change that by the reciprocal function. So I have 2 times secant squared. We're there, right? We have 2 secant squared. So we can say 2 secant squared x is equal to 2 secant squared x. We have proved it. Let me put this all together. We want to, maybe this would be a good point to screenshot it in case you haven't done it, or you also had trouble with it, you have it handy, you don't have to go through the whole video to find this one. All right, I'm going to change the page. Next question was number 9. So let's take a look at number 9. Before I move on, were there any questions on number 7?
No.
No, all right. Number 9. This one's ugly too. All right, so same deal. I want to pick one that looks more complex. So I'm taking a look at my left-hand side and a look at my right-hand side. Maybe left-hand side might be more complex, but right-hand side right now probably looks just as hard.
They're both
So
a little confusing.
they're both really ugly, really confusing, right? So there's no right or wrong answer to any of these, especially for this one. I feel like they're both just as ugly. So why don't we try working with the left-hand side? Okay. So we're gonna work with the left-hand side. Okay, let's try distributing. Maybe that will help us get somewhere. Well, does 1 plus cotangent squared give us anything? I see a square. Maybe it's worth taking a look. So go make sure you have this handy from section 5.1, that first page. That has all of your equations. So we had 1 plus, let me go back to, so you make sure you have this handy. You have your book. It was 9, right? And now 11. So I have 1 plus cotangent, and 1 plus cotangent does give us something, right? That gives you cosecant. Let's try changing it to cosecant. That's what 1 plus cotangent gives us. So right now we have tangent squared times cosecant squared of x. Hmm. Well, maybe that's all we want to do because we want to have this something being added, or in this case, subtracted. So maybe that's not the best case. So let's start over again. And that's going to happen sometimes. Sometimes we're working and we're like, nope, not the right step. Let's try distributing it. Okay, so if we distribute, we're left with tangent squared of x plus tangent squared of x times cotangent squared of x. Okay, I'm kind of stuck. So let's try writing in terms of sine and cosine. If we do, we have tangent is sine over cosine, sine squared of x over cosine squared of x plus sine squared of x over cosine squared of x times cotangent is a reciprocal, so that I have, the reciprocal. So I have cosine squared of x over sine squared of x. Well, we get something cool that happens, right? Here we see these cancel to make 1. They divide to make 1. So what are we left with? We're left with sine squared of x over cosine squared of x plus 1. Okay, so let's get a common denominator. So let's multiply this by cosine squared of x. So I can go ahead and add them. All right, if I do so, for my first term, I rewrite it sine squared of x over cosine squared of x, plus I'm left with cosine squared of x over cosine squared of x. Let's bring them together under the same denominator. So I'm left with sine squared of x plus cosine squared of x over cosine squared of x. We're almost there. Do you see it? Can you see the finish line? Okay, so we're going to use 2 Pythagorean identities. One of them is, we know that Pythagorean identities. That's what we're going to use. So we know sine squared plus cosine squared equals 1. Wow. And we're going to use that in our problem. So we're going to, using our rule, we're going to rewrite this so that our numerator is 1. So we're now left with 1. And what do we want? We want a denominator of 1 minus sine. We can do that, right? Again, we manipulate Pythagorean identity. We can move the sign over. I'm sorry, whenever I put my hand too far to the right, it moves it. Minus our sine squared. So cosine squared equals 1 minus sine squared. So I make the denominator 1 minus sine squared. And we are done. So this right here was our side work. And you can have side work, just so that you don't lose your train of thought.
So when you have a 1, you can input anything you want, essentially, as long as it equals 1, and you can use that to play with the other numbers.
And we have many things that equal 1. So what equals 1? Your Pythagorean identities, they all have a 1. You can manipulate it to whatever you want. There's 3 of them. You can even essentially throw in reciprocals. So sine times cosecant, that gives us 1. As long as we throw in a 1, we're not changing the value of it, even if it looks like it's something else.
But I'm just looking in the case of here where we had 1, and we because we wanted to get a common denominator, we just changed 1 to cosine squared over cosine squared. You could theoretically whatever happens to be added to 1, you can change 1 to have the same denominator and just make sure the numerator is the same.
Right. So your classmate's saying, hey, right here, I see that you just multiplied by a cosine square and a cosine square, and that fixed it. Yeah, well, what technique are we doing? Our technique is we're trying to get that same denominator, right? So you multiply to the top and bottom. So even if that weren't 1, I would still do that to get that same denominator. And the reason for that is because I want to be able to add those 2 terms together. But yeah, for this case, it was a 1. So that really didn't get you anywhere, but it did transform your 1 to be a cosine squared over a cosine squared. All right, so that was a good question. Any other questions? If you'd like to, this would be a good moment to screenshot it so that you have it handy, so that you can finish it off, or if you haven't done your homework, you have the work for one of them.
Can you address real quick that last little bit of work you did, how you ended up with the 1 over 1 minus sine squared x?
Yes, of course. Are you okay with what happened here? How we got there?
Yeah, I'm up to that point, yeah.
Okay, so from there, we're going to manipulate our Pythagorean identities. We're going to use the fact that we know, let me pick color that I haven't used. So we're going to use the fact that we have this Pythagorean identity. Now we can use any of these. Technically we have 9. There's really 3, but from each 3, we can spit out 2 more. So we're using this one to our advantage. Right? So our numerator, we see how we said that sine squared plus cosine squared, that's equal to 1. So if they're equal, I can replace that with a 1, which is how we got here. Now my denominator, I have a cosine squared, but what do we want? If you take a look at what you want a 1 minus sine squared. Now how can I get 1 minus sine squared from a cosine squared? Oh, well, I see that yet again, I'm using this Pythagorean identity to my advantage, right? I'm going to rewrite this Pythagorean identity so that I have cosine squared. What is that equal to? It's equal to 1 minus sine. So I can go ahead and change this so that I now have 1 minus sine squared. And that gets us to what we want on the other side. Now you have to really be best friends with the Pythagorean identity. If you haven't done so, maybe photocopy or take a picture of that first page from section 5.1. Just have it handy and maybe make it a point to go through your Pythagorean identities and take a moment to maybe recite them to yourself. Just study them so you see what the pairings are or how you can manipulate them. I mean, when we glance at them, we see them, we're like, okay, yeah, I got it. But maybe it requires a bit more of a brain effort. So make it a point to study them, to see them, to really see what they're saying.
I made a copy.
Yeah, beautiful. That's great. We should all have a copy, maybe have a picture of it in our phone, just so that we have it handy as we're working through all of these sections.
I'm really struggling with the difference of squares, though. I think that's what's killing me.
You know what? I figured that would be it, and so it was one of those correct pages you have to go over, but I haven't really made them an effort. So I think on Tuesday I'll make it a point to go over them together as a class, maybe with 2 of them on Tuesday. But I was gonna do it today, but I didn't feel like it was fair to just throw it at you last minute. So we'll do that on Tuesday because that's a very helpful tool. Okay, so let's move on to today's lecture. So as we move on through these sections, so we did 5.1 and 5.2, there are identities and proofs. We're going to go into 5.3, that's sum and difference, so that's new formulas, and from here on out, each section is going to throw at us new formulas. Now the purpose of this new formulas is to help us rewrite equations. We're rewriting these equations for several reasons. One of them is when we go into chapter 6, where we're solving equations, maybe it'll be set up in a way where we can't solve for our unknown, x, theta, beta, whatever variable we want, it might not always be written nicely. So we can rewrite it using these identities.
Professor,
Also, yeah,
sorry, really quick before you start today's lecture, I just had a question about the test. The graphing, have you, I noticed that when you graded it, the percentage didn't go up. Is it inputted on Canvas yet?
it should.
Because when I click on it, it says 13 out of 13, but it says pending professor approval. So, and my percentage also hadn't gone up since you had graded it. So I wasn't sure if like Canvas recognizes it as a real grade just yet. And I noticed that
Oh,
a couple of my classmates said the same thing too, that their graphing got graded. When you click on it, they have a percentage of the number out of 13, but their percentage didn't go up or down.
okay, let me take a look at that. Thank you for pointing that out.
Yeah, of course. And then the extra credit has that been graded as well or not yet?
No, I haven't input the extra credit yet.
No, I was just wondering before you started
Yeah.
today. Sorry about that.
That's okay. Good
I'm
question.
wondering if
No.
perhaps Canvas assumes that you're scoring 100%, so it's testing at 100%, and that's why your percentage isn't changing.
But
Oh, I don't know.
if you click on the graphing, it says pending professor approval. Like if you click on your grade, when you click on the app, if you click on the graphing part on the very bottom after you see the grade out of 13, it says pending professor something on the bottom. And if you could do what if scores. So if you what if it to what she inputted, it changes it. So you're actually able to actually input each grade as you go to see what if I got this on this test, how would my grade change? And I did that with the graphing part and it did go up. So that's why I was wondering, I don't think it counted as a real grade just yet. And when I clicked on it, that's when I noticed that it says pending professor approval on the bottom. And again, a couple of my classmates said the same thing, that their grade didn't go up or down. So yeah, that was my question, Professor. Sorry about that. Thank you.
No, it's okay. Thank you for letting me know. Otherwise, I wouldn't have known. So, oh no, I'll take a look at it after class. I'm trying to take a look at it right now. And
yeah, I didn't want to distract you with your lecture. I just wanted to bring it up to you.
no, thank you. I'll make a note of it. So check grades. That's weird. I have graded them and I have fixed them because there were, some of you might have had a test with a typo because everyone had different questions. Not everyone had a problem with the typo. And then so I fixed that. I also input grades for your graphing portion and I made a comment as to why you didn't get full credit, or I might have said great job, you got full credit. But yeah, I'll take a look at that so that your grade reflects your most current grade.
Alrighty, Professor. Thank you.
Thank you. All right, so let's continue with section 5.3. So this is getting you ready for chapter 6, but it's also getting you ready for calculus, because sometimes you might have to integrate or differentiate some equations that are not written in the method that we can work with. So how do we go around it? We have to rewrite it completely, and we rely on our formulas for that we learned from trade. All right, so 5.3. So just like before, maybe this is the page you want to have handy, or you want to go ahead and screenshot, or just having a picture of it in your cell phone as you're working through this, because you're going to be working with this all the time. So this is your whole section. Honestly, we can just say this is it. Let's go home, because that's it. We're going to work on how to rewrite it. So we have equality. You see these equal signs all here? Equality is very powerful. Like I said, I'm pretty sure I said it a million times before. It's powerful because it tells us not only can we go from left to right, but we can also go from right to left. We can work both ways, depending however what our question's asking or what we see fit. So let's read our text. The sum and difference formulas. Sine, cosine, tangent each have formulas for the sum and difference of two angles shown at the right. Each formula is an identity, but in practice, each is more about putting values into an equation, so it's treated like a formula. Now, the development or proof of many of the formulas identities introduced in section 5.3 are presented at the end of the section after the focus exercises. Okay, so these are our 6 formulas we're going to have handy. As we're working through them, I'm going to have a a copy of them handy just so we can refer back to them. And I'm going to refer to them by number. So let's do example 1. Find a counterexample for A and B to demonstrate this equation is not an identity. So I don't worry so much about counterexamples, but that's what's important about an identity, that it has to hold true always. And notice it's pretty much trying to treat this like if you distribute, and that's not what's going on. Cosine is a property or an act that's acting on an argument. So arguments do not work like numbers and variables. We treat them differently. It's an argument. Okay, so in class example 2, discuss similar and distinct features between the formulas. So we can do that here. And it's just a point of taking a moment to look at them, see how they're different and how they're alike. Let's focus on the first two, the cosine ones. So we see, hey, they look pretty similar. They have cosine of A, cosine of B, cosine of A, cosine of B, sine of A, sine of B, sine of A, sine of B. But what's different? We see that when I have a minus in the argument, it's a plus in our other side of our argument. When I have a plus in my cosine, in my extended form, I have a minus. So that's something we keep track of, right? What about sines? Okay, so we see that they're similar as well, right? I have sine of A, cosine of B, sine of A, cosine of B, sine of B, cosine of A, and sine of B, cosine of A. So they're very similar, but unlike cosines, if I have a plus, I have a plus, and a minus, I have a minus. So that's one way I can think about it, of how they're similar. That's what I wanted us to do for example 1. Take a moment to look at these equations. All right, now on to the next page. In each formula, A and B represent any degree or radian measure. So we can work with these in both degree and radian measure. For example, cosine of a difference formula using x and y or alpha and theta is just valid. So here we have our cosine of a difference. Let's demonstrate this formula identity. It's true by choosing unit circle values already familiar to us. So use a cosine of a difference formula to find the exact value of 120. So if you look in your unit circle, you know what this is. It's a value in your unit circle. So we're going to use these to evaluate or work with numbers that are not in our unit circle without having to use a calculator, so we can give an exact solution. All right, procedure. We already know that cosine of 120 equals -1/2. So we're just demonstrating that the formula is valid. Second, identify two familiar unit circle angle measures which have a difference of 120 degrees. Let's choose 150 and 130. Other options work just as well. Use a cosine difference formula to evaluate. So what this is saying is we want to find the value of cosine of 120. This one is just setting us up to work with this because I know what cosine of 120 is, right? You look at a unit circle, that's a point in a unit circle, 120 degrees. Well, let's say I want to use one of my cosine formulas, particularly the one we just learned. This cosine of a difference. So I want to think, hey, what numbers can I work with so that when I subtract them, I get 120? Well, isn't 120 made up of 150 minus 30? Yeah, that gives us 120. So let's go ahead and separate this to be cosine of 150 minus 30. All right, now let's go ahead and use our formula. If we use our formula, cosine of a number minus a number is, well, we have it in front, right? When I want to subtract, I want to take cosine of my first number times cosine of my second number plus sine of my first number times sine of my second number. So that's what we're going to do. So we have to write it this way using our formula. So by formula, that's what we have. And now I can look and evaluate each one differently. So make sure you have your unit circle handy. Cosine of 150 is negative square root 3 over 2. Cosine of 30 is radical 3 over 2. Plus sine of 150 is 1/2 and sine of 30 is 1/2. All right, from there we just add our fractions and multiply. So for our first one, we get radical 3 times radical 3 is just 3. And we have that negative over 4 plus 1 over 4, we get negative 2 over 4. We simplify, we get negative 1/2. Now let's do example 4. Take a look at your unit circle. Is 15 a value in your unit circle? No, it's not. We go by 30s, 45s, and 60s, and values in different types of 30s, 60s, and 45s, and 90s. We don't have 15. So how can I find cosine of 15? Well, think of any two numbers that give you 15. So 15 can be written in many ways. 45 minus 30, 60 minus 45, 225 minus 210, whatever you can think of that works is fine, as long as when you subtract, you get 15. So start by expanding the expression using cosine of a difference formula. Let's use 60 minus 45. A nice little hint, if you can keep it in your first quadrant, that'd be better, because you don't have to worry about when it's negative and when it's positive. All right, so we can rewrite this 15 to be 60 minus 45. Now I can go ahead and use my formula. Now he doesn't write it here, but it's always a good practice to write down your formula. So this is coming from cosine of A. So this is A and this is B. This comes from cosine of A times cosine of B. It's a minus, so we'll write plus sine of A times sine of B. And this is where this formula comes from. Where that equation comes from our formula in our first page. So if 60 is A and 45 is B, we're going to make those adjustments. So I have cosine of 60, which is my A, cosine of my B, which is 45, plus sine of my A, which is 60, and sine of my B, just like we have above, right? We're just filling in those A's and B's. Now you want to take a look at your unit circle and see what values that holds true for. So you take a look at your unit circle and you evaluate. Okay, so that sine of 60 is 1/2, cosine of 45 is radical 2 over 2, plus, make sure you write down your plus, and we have sine of 60 is radical 3 over 2, and sine of 45 is radical 2 over 2. Now we multiply. Remember, you multiply your fractions across. 1 times radical 2 is radical 2. 2 times 2 is 4. Boom. Plus, multiply across. Radical 3 times radical 2, we get radical 6. 2 over 2, we get 4. Awesome. Last piece we have to add. This adds to be radical 2 plus radical 6 over 4. It makes it much easier if you go ahead and write down your formula as you're working with it. That's always recommended. It's very helpful. Okay, here we have some other formulas. These are your co-function formulas. So from the cosine of a difference formula, we can generate the following formulas. So that cosine of 90 minus a number is the same thing as sine of that number. So whatever this is, I can write it with just sine. Cosine of b plus a number is just the negative sine of a number. And sine of 90 minus a number is just cosine of that number. Sine of 180 minus a number is just sine of the number you're subtracting. Now here, these are your odd and even functions. So if I take cosine and that value on the inside is negative, it would be the exact same thing as if there were no negative. And that's so cool. Sine, if I have sine of a negative argument, it would be the same thing as just taking the negative and writing in the front. Same thing for tangent. If I have the negative of an argument, it's the same thing, just taking the negative and writing in the front. So this is why we say that cosine is even, because even if our argument's negative, it splits up positive, and sine and tangent are odd. All right, in class example 5, use the cosine difference formula to verify each identity. Okay, so here you want to use the formulas you have in page 1. So these formulas we have here, we want to use them to show them how our co-function identities hold true, now that we know how to verify. So let's do 5 together. In class example 5, let's do stat 7-1. Okay, well, I want to show that the right-hand side equals the left-hand side. Okay, so we can use one of our sum and difference formula. So we can say something like by difference formula. And let's write that formula. So our difference formula would be cosine of A minus B is equal to cosine of A times cosine of B plus sine of A times sine of B. Let's make A 90. Let's make B B. Let's go ahead and replace that with our function that we have here. Cosine of A times cosine of B plus sine of A times sine of B. If we do so, we're left with cosine of 90 times cosine of B plus sine of A, which is 90, sine of 90 times sine of B. Okay, let's evaluate these. We can take a look at a unit circle. What's 90? What's cosine at 90?
0.
0. So we're left with 0 times cosine of B. And we have plus. What's sine at 90?
1.
1 times sine of B. Okay, what is anything times 0? 0, right? So we're left with 0 plus 1 times sine of B. What's anything times 1? It's itself. So we're just left with sine of B. We had just proven this equality above. It checks out, they're equal. So now that we know our sum and difference formulas, we can take these co-function identities as given, because we know they will check out using our difference and sum formulas. Because of that 90, it's going to make some value 0, and thus it simplifies to whatever we have on the other side. All right, let's go ahead and move forward. The sign of the cosine and sum formula. We saw at the beginning of the section, the cosine of a sum is very similar to cosine of a difference. And we have this formula listed above. So go ahead and do this example. Well, let's do example 6 and then you can do the try one. They're right next to each other. So we want to find cosine of 105. And the problem is that if I take a look at my unit circle, there's not a 105 anywhere. I have 30, 60, 45, 90, 120, 135, 170. I'm sorry, 150, 180. No 105. So can we think of two numbers that give me 105? And you can play around with the numbers. So I have to maybe work with a 45 because the 45 will give me that 5. So maybe 150 minus 45. Yeah, that worked out. You can think of any mixture of numbers. So we're going to use the fact that we know that 150 is the same thing. I'm sorry, I wrote that wrong. 105 is the same thing as 150 minus 45. So I'm going to make a note. That's going to be my A, and that's going to be my B. Now, because we're using subtraction, we want to use the one that has a subtraction. This one has an addition. So if it wants us to use that one, we can think of another number that gives us an addition, right? So maybe I didn't think this one too clearly because it's guiding me to do it some way. In the future, once we're done with the section, you can use any one you want, addition or subtraction. So what two numbers can I add to get 105? So I know 45 will be one of them. 45 plus 60. And the reason why we did it is because I want to use my sum, cosine of a sum. Okay, keeping that in mind, I want to rewrite cosine of 105, letting A be 45 and B be 60. Let's take the time to rewrite our formula. Cosine of A plus B is equal to cosine of A, cosine of B, minus sine of A, sine of B. Let's go ahead and make those substitutions. So cosine of A, what is my A? I said A is 45. The cosine of 45 times, all right, what is my B? My B is 60 times cosine of 60 minus sine of A, what is A? 45. Sine of 45 times sine of B, and sine is 60. Okay, let's take a look at a unit circle and evaluate these values. Cosine of 45 is square root of 2 over 2. Cosine at 60 is square root of 2 over 2. Minus sine at 45 is, well, I think I messed up on cosine of 60. Cosine of 60 is 1/2. Sine of 45 is square root of 2 over 2 times sine of 60 is radical 3 over 2. All right, let's multiply across. Square root of 2 times 1 is square root of 2 over 2 times 2 is 4 minus square root of 2 times square root of 3 is square root of 6 over 2 times 2 is 4. We have the same denominator, so this simplifies to be 2 square root of 2 minus square root of 6 all over 4. Let's go ahead and box these. That's our answer. Okay, now let's go ahead and do you try it too. Let's have you try it. So I want to find cosine of 75. So what two numbers, I'll leave this for you to do. I just want to set you up. So what two numbers can you think of so that when you add them, you get 75? Because 75 is not a value in our unit circle, and I want to find the exact value. So with that said, go ahead and do you try it one. I'll give you a minute to do it, to get started. Okay, can't give you more than a minute. I got sidetracked. Okay, so what two numbers, and I want a response. What two numbers do you think of that work to, when you add them, you get 75?
30 and 45.
30 and 45. Cool, thanks. All right, now I'm going to use that sum cosine of a sum formula that you have right here. Let's write it down. I always emphasize to write down your formulas before you start for two reasons. One of them, so that you get more familiar with them and you kind of in a sense how to memorize them. Second, it's less likely for you to make a mistake if you have the formula right above you, because you're constantly checking, making sure your formula is matching up. It's matching up to what you have right above. And I always do it because I make mistakes all the time. So when you know you make mistakes all the time, you're more conscious of it so that you try to avoid them. That really is me. I would think very rarely do I ever earn 100% on an exam because I always made those silly mistakes. Okay, so let's go ahead and work this out. So we're saying that my A is going to be 30 and my B is going to be 45. Okay, let's make that replacement. So that we have cosine of A, which is 30, cosine of 30 times cosine of B, which is 45, minus sine of A, so sine of 30, times sine of B, sine of 45. Okay, cool. Now I can go ahead and find each one separately using our unit circle. So make sure you have your unit circle handy. You guys are very lucky. Well, not really, because it's not the ideal situation, but you're lucky that you have this online and I'm not heavily monitoring what you do. And if there were a live class like we originally were, I wouldn't give you the unit circle. You would have to build it on your own or have it memorized. But make sure you have a printout of the unit circle handy. So cosine of 30, that gives us square root 3 over 2. Cosine of 45 is square root 2 over 2 minus sine of 30, we get 1/2, times sine of 45, square root of 2 over 2. Okay, now let's do some algebra. Let's multiply across. So that we get square root of 3 times square root of 2, we get square root of 6. 2 times 2 is 4, minus 1 times square root of 2 is square root of 2. 2 times 2 is 4. So we're left with square root of 6 minus 2 all over 4. That is our answer. Were you on the right track? Are there any major questions about these formulas? All right. What happened?
I said no. That matches up with what I got.
Okay, cool. All right, let's continue. So we have a sum of difference formulas for sine. Okay, I think you're a pro. So having them handy, you have full liberty. And because of this, we might have different in-between work, but our answer is gonna work out the same. It's one of those beauties of math that if you're following the steps, you end up with the answer. So we have two different formulas to add to our list. We have sine of sum and difference. So you're trying to you try it too. So you have options. You can think of two numbers. So when you add them, you get negative 15. Or you can think of two numbers. So when you subtract them, you get negative 15. So let's do this. You try it too. I think subtraction would be cooler because I don't have to worry about throwing in negatives. So I want you to do for you try it too, I want you to think of two numbers. So when you subtract them, you get negative 15 and finish off the problem using this sign of a difference. That's subtraction formula. So go ahead and do your try it too. I'll give you about a minute to get it done. Okay, let's see where we're at. So what two numbers can you subtract to get 15? Negative 15. So can someone chime in on what numbers they chose?
30 and 45.
Cool, 30 and 45. So I'm going to let 30 be A and 45 be B, and I'm going to use this formula. So this tells me that sine of A minus B is equal to sine of A cosine of B minus sine of B and cosine of A. Okay, let's go ahead and work it out. All right, sine of A is 30, so sine of 30. Cosine of B is 45, because my B is 45, minus sine of B, my B is 45, times cosine of A, my A is 30. Okay, now we're going to use our unit circle to find these values. Okay, sine of 30, at 30, sine is 1/2, times cosine of 45, the square root of 2 over 2, minus sine of 45, square root of 2 over 2, and cosine of 30, that gives us square root of 3 over 2. Let's multiply. We're left with square root of 2 over 4 minus square root of 6 over 4. So our answer is 2 square root of 2 minus square root of 6 over 4.
Quick question.
Yeah,
Can you also do this with 300 minus 315?
yep, and you should get the same answer.
All right, thank you.
Yeah, and that really again just shows you the beauty of math, that you can pick any two numbers, and as long as the sum or the difference is what you're trying to work with, in this case it's at negative 15, as long as it holds true, then you should get the same answer. And if for some reason we didn't, then we have to be careful and maybe check our algebra. And you can pick whichever one you wanted. Now, why did I aim you to do subtraction? Well, that way you don't have to work with a negative value for A and for B to get your work done. If you try to add to get a negative, you have to make a negative. So maybe negative 45 and 30. So then you have to work with negative degrees, and that would move your quadrants around. So whenever possible, you want to work with positive values or values that are within the first quadrant. That won't always happen, but if possible, that'd be ideal. Okay, in class example 8, use sine of a difference formula to show that a sine of an angle is equal to its supplement. We're going to skip that one. Reading from left to right. It isn't necessary that an identity be read only from left to right. We can read identities from right to left as well. For example, the cosine of a difference formula. So it's just swapping it right here, right? So that you read it also from right to left. And we can also do that. For example, it can be simplified that cosine of 50 minus 120. Well, I can't find 50 and 120 in my unit circle, so I can subtract them so that it gives us cosine of 30, and we can work with 30. Even though we don't know the individual cosine values of 50 and 20, when written in the correct expanded form pattern, we can evaluate the cosine of their difference. So for example here, example 9, if we take a look at this, we're like, whoa, how in the world do they want us to find these numbers? In our unit circle, we do not have 110, nor do we have 170. But then you're like, oh, okay, I can rewrite this. This is the same thing as my cosine of difference. So I can rewrite this to be subtraction. Cosine of 110. So again, you have to take a moment to label your A and your B. So if this is A, and this might be according to my formula, then this looks like cosine of A minus B. So cosine of 110 minus 170, which is negative 60. I can find 60 in my unit circle. I can definitely find negative 60 in my unit circle. So that gives me 1/2. All right, so let's go ahead and do example 10. Same idea. I have cosine and sine, cosine and sine. So which one is this? Which formula is this? This is our sum of sine. That's why we had to take the moment to look at these. I'm going to jump to the first page. They all kind of look alike, so you kind of have to take a moment to know how they differ. For my cosines, it's always cosine and cosine, sine and sine. So if those two pairings are together, we know it's a cosine. And then you have to look at your sine in the middle to know if it's difference or sum. Now for sine, notice your pairing is opposite. We have sine and cosine, sine and cosine, sine and cosine, sine and cosine. The sine in the first term carries your A, the cosine will carry your B. And you notice that if it's a plus, we write a plus. So if it's a plus, we want to make sure to write it with a plus. Okay, so having this fresh in our mind, let's jump back to the example we're doing. So with example 10, I have cosine and sine plus cosine and sine. Okay, when I have different pairings, I know I'm working with the sine one. That's always important to take a moment to look at them. Because I have a plus, I know it's a sum. So our formula that we're going to work with is our sine of sum. So I know this is sine of A plus sine of B. I'm sorry, B. And that's what we have here. That's our A and that's our B. And we can add them. When we add them, hey, that's the value in the unit circle. And that's so cool because then I can tell you what that is. So sine at 315 is negative square root of 2. Okay, let's take a moment to look at these you try it questions. All right, so let's take a moment to think about how we would do this one. I have sine and cosine. When I have those different pairings, I know it's going to be a sine equation. All right, I have a minus, so I know it's going to have a minus because my sign doesn't have the opposite sign. Okay, now for the first term, the sign carries your A. So that's going to be my A, and that's going to be your B. So I have 100 and 160. Okay, now we can go ahead and work with our formula. So our formula tells us that we can subtract. So 100 minus 60, like 160, that gives you negative 160. So we can work with, what is sine at negative 60? I can evaluate that. I know what 60 is. And if you don't like working with negatives, change it to a positive. Add 360. Negative 60 plus 360. You get 300. That would be the same thing. What's sine at 300? And we get negative square root of 3. So that would square root of 3 over 2. That would be your answer. So that's how we can go around values that do not have a point in our unit circle. So that 160 and 160 are not in a unit circle. That's how we can go around it. Okay, I'm kind of dragging this long, so I'm going to go ahead and speed through it. Moving forward, sum and different formulas with radian values. Now, this is probably not the right thing for me to say, but I do not like working with radians. And that's not ideal because we're going to have to work with radians at some point. So if you'd like to, it wouldn't be incorrect to change it to radians. And again, that's a preference thing. So moving forward, when we add and subtract radian values, it is common for them to have a denominator of 12, common denominator of 12. This means it is important to see the familiar radian values with the denominator of 12 as well. So in class example 11, write each common radian measure with a denominator of 12. And the reason why I want you to do this is because you can write them all with a denominator of 12, because they all have a denominator of 3, 4, and 6. So the lowest common denominator would be a 12. So in class example 12, find pi over 12. Well, if you look at unit circle, our smallest value is pi over 6. There's no pi over 12. But we can get pi over 12 from 4 pi minus 3 pi. Sorry about that. And that will give us pi over 12. So we do the same work, but with the radian measure. And again, if you do not like radian measure, feel free to change it to degrees for your personal preference. Okay, so we have cosine of 7 pi over 12. How can we get 7 pi over 12? Well, maybe you'll be worthy of doing this chart on the side. So let's go ahead and do this chart on the side. Let's change them all to a denominator of 12. So we change this to times 3 over 3. That'll give us 3 pi over 12. We multiply it by 4 over 4. That gives us 4 pi over 12 times 6 over 6. 6 pi over 12. Multiply it by a 4. 8 pi over 12 by 3. 9 pi over 12 by a 2. 10 pi over 12. And if we multiply it by 12 over 12, we get 12 pi over 12. Now, why did we do this? So when you're working through your problems in your example, you have all of your measures written with a 12, so you can easily add and subtract them. Okay, so looking at these numbers that we have here, oh, I'm missing one, that we have here, what mixture of them can we use so that when I add them, if we wanted to add, we get 7 pi over 12. And if we look at them, maybe 3 and 4, that gives us 7. So we have 3 pi over 12 and 4 pi over 12. Okay, so can you write this as cosine of 3 pi over 12 plus 4 pi over 12. And now I can use my cosine sum formula. And I'm going to erase that circulated. So maybe this is worth having, right? So you can easily work through it. All right, so we have cosine of 3 pi over 12 plus cosine of 4 pi over 12. We're going to use our formula. So if we use our formula, let's write it down. We have cosine of A plus B. And that is equal to cosine of A times cosine of B minus sine of A times sine of B. And that's our cosine sum formula. So if we let this be A and we let this be B, let's go ahead and make that substitution. So cosine of 3 pi over 12 times cosine of 4 pi over 12 minus sine of 3 pi over 12 and sine of 4 pi over 12. Ah. Okay, we need to simplify these fractions, right? But we already have them simplified on the right here in the right hand side. So 3 pi over 12 is pi over 4. So I have cosine of pi over 4 times cosine of pi over 3 minus sine of pi over 4 times sine of pi over 3. And now we use our unit circle. At pi over 4, cosine is square root of 2 over 2. Cosine at pi over 3 is 1/2 minus sine at pi over 4. That gives us square root of 2 over 2 times sine at pi over 3. That gives us square root of 3 over 2. And then we multiply, we get square root of 2 over 4 minus square root of 6 over 4. They have a common denominator, so we can write it as square root of 2 minus square root of 6 over 4. All right, tangent. So same story. We're going to have these formulas, and we have them highlighted. We have numbered 5 and 6. We have these formulas for tangent, and we can use them both ways. We can take it so that we can evaluate for a value that's not a unit circle, either by adding, subtracting, working both ways. So let's take a look at example 13. Use a tangent sum difference formula to find tangent of 15. Rationalize the denominator. Okay, so the same problem here as we had before. 15 is not a number in our unit circle. So I want to think of two numbers when either I add or subtract them, give me a 15. And there's no right or wrong here. So here we see that 45 minus 30, 60 minus 45, 225 minus 210, they all give me 45. Just a matter of what you like to use. So let's do 45 and 16. Now, where to use those numbers? Try to think of what numbers you like to work with. This here, he said, the best values to use are the ones without fractions. So let's try 45 and 16. So we write tangent of 60 minus 45, tangent of 60 minus tangent of 45, and we're just sitting up for our formula above, right? So this formula here. Tangent of A minus tangent of B over 1 plus tangent of A times tangent of B. We're just replacing values. Okay, tangent of 60 gives us radical 3. Tangent of 45 is 1. Over 1 plus tangent of 60, which is square root of 3, times tangent of 45, which is 1. All right, we go ahead and simplify. So we just multiply here. That just gives us radical 3. So we have radical 3 minus 1 over radical 3 plus 1. And then we can multiply by the conjugate because we don't want to have radicals in our denominator. So we multiply by the conjugate. I'll highlight that in blue. So our numerator will have to FOIL, and we're left with 3 times 2 squared root of 3 plus 1. And our denominator, it's just our denominator squared. I'll do the work for you here on the side. So what's going on? So we have to FOIL our numerator, meaning we have to multiply radical 3 times radical 3 gives us radical 9. Radical 3 times negative 1, negative radical 3. Negative 1 times radical 3, negative radical 3. Negative 1 times negative 1 gives us a plus 1. All right, so what does my numerator simplify to? We have square root of 9. I have 2 of these, so minus 2 square root of 3 plus 1. Square root of 9 is 3, so 3 minus square root of 3 minus 2 square root of 3 plus 1, and 3 plus 1 is 4. So I have 4 minus 2 square root of 3, which is what we have right here. What we have right there. Now what happened in my denominator? All right, in my denominator, I have to multiply those two denominator numbers. So we have square root of 3 plus 1 and square root of 3 minus 1. So notice they're conjugates of one another. And that's very cool because when I multiply, I can do this without having to multiply. I can take your A value and your B value and square them. So square root of 3 squared minus your B squared, 1 squared. So this gives us 3 minus 1, which just gives us 2, like we have right here. All right, so now we're there. Last piece, remember this 2 is, if it's helpful, draw a heart. It's dividing your first term, so 4 divided by 2, and it's also dividing your second term. So that's how we have it split right here. 4 divided by 2 gives us 2, and here these 2's divide to make 1, so we're just left with radical 3. I know you might think it's really silly that I'm drawing a heart every time, but it's really to show you that we need to remember that 2 divides each term in your numerator separately. All right, that's it for this section. Before we leave, let's do some problems together. So your homework is, I want to do all the odd problems. I think that sounds fair. Maybe not all of the odds. No, we can do all the odds. So before we leave, I want us to do, let's do 17. And 7. All right, so your homework for 5.3 is all odds. But before we leave, let's do 7 and 17. I'll give you 3 minutes to get started, and then we'll go ahead and meet together. I'm going to step away, so if you ask a question, I won't be here. I'll be back by the 30-minute mark. Okay, so hopefully you had a chance to start these problems. Okay, let's go ahead and continue. I had lost the screen share for a second. So let's work with number 7. And I wanted to do number 7 because we didn't do enough of those tangent problems. So the problem here is I want to find the exact solution I want to evaluate, but 195 is not a value I unit circle. So let's think of two numbers. So when I add them, I get 195. So maybe 60 plus 45? No, but 135 minus 60. No. So what numbers did you work with? Save me the trouble of playing with my numbers. One 50 plus 45?
Yeah.
Yeah. Okay, so we get 185 plus, so it's 150 plus 45. And you can pick any two numbers that you want. So that my A will be my B, my A will be 150 and my B will be 45. Okay, let's go ahead and write down our formula. So for tangent of A plus B, tangent of A plus B is equal to tangent of A plus tangent of B all over 1 minus tangent of A times tangent of B. So we said our A is 150 and our B is 45. Okay, 150 is in quadrant 2, so tangent will be negative. So tangent of 150, so tangent of 30 is square root of 3 over 3. So we have negative square root of 3 over 3 plus tangent of B, which is 45. Tangent of 45 is 1 all over 1 minus tangent of A. Tangent of A is 150, which we said was square root of 3 over 3 negative times tangent of B. Tangent of 45, we said that was 1. Okay, so let's simplify our numerator. So if we get a common denominator, we can multiply that by 3 over 3, and we're left with negative square root of 3 plus 3 all over 3, all of which is being divided by, now we need to clean up our denominator. I can multiply it by 1, which just makes a negative 3. So I have 1 minus negative square root of 3 over 3. Okay, let's multiply our 1 by 3 over 3. So we're still cleaning up our denominator. I have negative square root of 3 plus 3 over 3, all of which is divided by 3 over 3 plus square root of 3 over 3. So that we get negative square root of 3 plus 3 over 3 all over 3 plus square root of 3 over 3. Okay, because we have the same denominators in the top and bottom, those will cancel. So that we're left with negative square root of 3 plus 3 all over 3 plus square root of 3. And that's our answer. Even though they're the same numbers, top and bottom, it's tempting to just say it's 1, but that negative in the front of the radical 3 makes it different. So that's our answer.
Can we, sorry, can we go
Uh-huh.
over that one more time?
What part?
Uh,
All of it?
yeah.
Yeah, okay. Well, before even going over it, we can think of your numbers more strategically. So I kind of didn't set you up for that because I just think of any two numbers. But maybe with tangent, they did make a point in your book where they said they work with numbers that do not have a fraction. So if you look at your chart at your unit circle, so let me share with you. When you have your unit circle handy with you, and we did charts with these too, there are some numbers that are nicer because they don't have fractions, only with tangent. So let's take a look at analyze this chart for a minute. We see that for tangent is here, there are some numbers that don't give us fractions, particularly 0, 45 angles, and 60 angles. So maybe we would have liked to work with angles that didn't give us a fraction. So if you want to spend more time playing with your numbers, those are numbers they want to work with. All numbers that have a 45, so that second tick mark, and all numbers that have a 60, so that third tick mark. Those are numbers that you would like to work with tangent because they won't result in fractions. But we didn't do that, so let's go back to the problem we're working with. And we will try to walk you through it. Okay, so we have tangent of 150 and tangent of 45. So are you okay with what we did in black, or we just plug them in?
Yeah, I have all that set up, but it's the actual algebra that I was.
The algebra, I know, the algebra. Okay, so we have to, let's work with our numerator and denominator separately. Maybe that will be helpful. So for our numerator, we need to simplify our numerator. Let's simplify as much as we have. We have negative square root of 3 over 3 plus 1. Okay, well, I need to add them, but before I do that, I need a common denominator. So let's multiply by 3 over 3. We can think of it as over 1. So we now have negative square root of 3 over 3 plus 3 over 3. Okay, great. Now I have a common denominator. I have negative square root of 3 plus 3 over 3. Great, that's my numerator. Now let's take a moment to simplify your denominator, which was more complicated. All right, in our denominator, we have 1 minus square root of 3 over 3. That's what we want to work with. I'm sorry, 1 minus. 1 minus negative square root of 3 over 3 times 1. That's what we had. Okay, so let's take a moment to multiply in the parentheses. If I multiply them, because I'm multiplying by 1, it's just negative square root of 3. All right, so I have 1 minus negative square root of 3 over 3. A negative times a negative, that gives a positive. So let's just rewrite it. So we have 1 plus square root of 3 over 3. Same deal, we need to get a common denominator so we can add. So let's multiply it by a 3 over 3. Let's write 1 as 1 over 1. So we get 3 over 3 plus square root of 3 over 3. Great, we have a common denominator. So I have 3 plus square root of 3 over 3. So now I have my denominator and my numerator. Let's write them together, which is what we have here. All right, when we work with complex fractions, if they have the same number in the denominator, they're going to cancel out to make 1. So we cancel out in green those 3's. So for our final answer, we're left with negative square root of 3 plus 3 over 3 plus square root of 3. Now you might think, hey, that negative, I can just make it negative 1 because we have the same top and bottom. But that plus and that minus unites them, so you can't break them up. Think of them as like they're married. So you can't break them up. Because even if we try to factor out negative 1, it changes the entire setup. Now we have square root of 3 minus 3. So we can't ignore that negative 1. It's attached to only the 3, not the product of radical 3 plus 3. So therefore, that would be our simplest form.
Got it.
Now, actually, yeah, you're welcome. Now, actually, as I'm talking to you about this problem, I shouldn't box it. It's still incorrect. Not incorrect, but we still have more work because we have a radical in the denominator. So there's still more work to do. It's not our final answer. I have to multiply by the conjugate so I can get rid of that denominator. So one last step. I have to go ahead and multiply by, take a look at your denominator, write those same terms but opposite sign. So I have 3 plus radical 3. I have to multiply by 3 minus radical 3 to rationalize. Okay, in our numerator, we have to multiply. Oh, that's going to be so much work. So we have to multiply these two binomials. So I have radical 3 times 3. That gives us negative 3 radical 3. Negative radical 3 times negative radical 3 gives us plus square root of 9. 3 times 3, you get plus 9. And lastly, 3 times negative radical 3, you get negative 3 radical 3 for my numerator. And my denominator, it's my first term squared minus my last term squared. So I have 9 minus 3. All right, let's clean this up. So I have two of those radical 3's. Sorry about the train. So I have negative 3 plus negative 3, it's negative 6. We have negative 6 radical 3. And we have 9. This is equal to 3. Square root of 9 is 3. 9 plus 3 is plus 12. That's my numerator. And your denominator, 9 minus 3 is 6. Now always draw your heart, no matter how silly you may think it is. The 6 divides the 12, and the 6 divides that negative 6 minus 3. So our final answer, negative 6 divided by 6 is negative square root of 3, and 12 divided by 6 is 2. So we can rearrange our terms so that I have positive 2 minus square root of 3 for our final answer.
That's a mess.
That is a mess. This was just side work. Let me highlight that as side work. Where are side work start and end? Here. That is a mess. There's talk about marriage and hearts, and that's all in a day's work and trig. Right, I'm so sorry, but yeah, that is a mess. Your algebra will be challenged. So why don't you make it a point to make sure you do all of those problems, and the ones that you're like, yeah, that algebra was weird, you can always do them before class or in the beginning of class next session.
Yeah, sounds like a good plan.
Yeah. And also make sure you check your work. You can check your book at bobpryor.com where your answer is. All right, next one I wanted us to try was 17. Okay, so we see sine and cosine, sine and cosine. When they're different, our pairings, we know that it's going to be a sine because cosine has cosine, cosine plus or minus sine, sine. So I know for sure this is going to be a sine. So I'm setting up my thought process. And my middle sign's a plus, so I know it's going to be plus these two numbers, whatever they may be. Okay, so what are our two numbers? Is 13 pi over 20 and negative 3 pi over 20. Now we have a problem here because I don't have any denominator over 20 in my unit circle. So I can't evaluate each one in my unit circle. That's not going to happen. I can't do so. We could with the use of a calculator, but up until now, we haven't introduced a calculator. We're using the unit circle in our brains. Okay, well, let's try and add this up. Maybe that'll give me a number that's within my unit circle. So let's go ahead and add this up. So we have 13 pi over 20 minus 3 pi over 20. Okay, 13 minus 3 is 10 pi over 20. All right, that reduces, right? 10 over 2 gives us 1 over 2. Oh, that's just pi over 2. Do we know sine at pi over 2? Yep. We take a look at unit circle. Pi over 2 is at halfway, that 0, 1 point. Sine is y, so this is forced to be 1. And that's my answer. Alrighty. So I'll leave you here. I assigned the odds. Give them a try. If you have any questions, ask me. You can email me. I'll be happy to help. So that's it for today. On Tuesday, I'll send you an email. We'll work through some problems together from our correct portion, our review portion. I'll email them to you after class. Now, something else I'm going to do is I am going to open up your quizzes for a couple of hours, and then I'm going to delete them. So your quizzes, let me go ahead and share. Your quizzes, I'm going to delete them because they are an accessibility issue because I need to add a name to each picture. So when you graph, there's some of them that have a picture. So I'm going to delete them. But for those of you that didn't get a chance to finish your quizzes, I'm going to open them up until 7. After that, I'm going to close them and delete them. I'm going to save your score. So I'll export my gradebook. I'll save your score and I'll manually enter them, but there'll be no more quizzes for that for me to open up in the future. So if you're missing a quiz, I'll open it up from now until 7.
So
And I'll do that right now.
All these quizzes
For each section,
for 5
chapter 4.
Sorry, for chapter 4.
For chapter 4, chapter 5, we're in the middle of chapter 5, right?
Yeah.
So I'll leave chapter 5 quizzes open because we haven't done so. But I'm going to delete chapter 4 quizzes. Thank you for bringing that up. I didn't think about chapter 5. I'm going to delete chapter 4 quizzes because every image I have, I need to caption it, and that's like 500 images, and that's too much work. And so I'm going to delete them, but I'll save your score. And in case you never got to it, I don't want you to feel like you missed out. So I'm going to open up all your quizzes from now until, did I say 7 or 8?
I heard 7. 7 being 7 tonight.
7 tonight, yeah. In case you didn't get to it. If you finish all your chapter 4 quizzes, you're fine.
Okay, but I still have time to do the chapter 5s though. Is that?
Oh yeah, those will be open until your next exam, whatever I said it would be.
Gotcha.
Don't worry about chapter 5. That's for those of you who didn't get to chapter 4. Alrighty, so that's it for today. I'll open them up right now and I'll send a mass email to let everybody know what I'm going to do with chapter 4 quizzes. All right, well, have a nice day. If you have any personal questions to ask me, you can always email me.
Just the graphing though, you were gonna look into it, right? Just to see if it...
Yeah, because it says that you're still waiting for a score from me, I will do that.
Okay, sweet, thank you.
No problem.
Just when I did the what if score, I did the what if score and I manually typed in 13 out of 13 and my percentage did go up. Granted, it was a little bit, that's why I was wondering, like, if I do the what if score and I type in the score I got, why does it still go up? That was my...
Okay, yeah.
All right, thank you, Professor. Take care.
No problem, take care. All right, I'm gonna log off, bye.